When you store a bunch of variables, like let's say you create an array and you store an array in memory, big endian just means that the next array elements are in order of increasing memory address. Little endian means that they actually go backwards in memory, okay? And different computer systems use different architectures, just depends on what you want and how it's set up. And we'll actually see which system which structure my system uses in a second. So we're going to add 1 to the pointer, and now we're going to access something. What are we going to find? Who knows? I was pointing to x1, and then now I just pushed the pointer somewhere else in memory. And we're going to type its value. We're going to show what its address is, and then we're going to show its value. So let's do it. Uh-oh. Oh, that works. Okay. Let's see. Okay, so we started out pointing to hex 28FED0, all right? And we knew that we put 25 there, and so that's fine. Then we changed its value to 5, so that's fine. And then this is the line where we take the pointer and add 1 to itself. And notice that now, when we do that, we're at hex 28FED4. All right, and the value there is 2,686,672. Some garbage memory. Some junk memory. Now, what I've just shown you should maybe get you thinking about, like, we pointed to a variable, x1, and then by pointer arithmetic, I'm able to push that pointer into another space in memory that I'm accessing data that is not even part of my program. You see that? Like this isn't x2. x2 we set to -10 or something like that. This is just some other variable that happens to be, oh, and by the way, remember we said that this would, adding 1 to it would push the pointer 4 bytes ahead in memory? We said that, remember that? Check it out. We were at 28FED0, and now we're at 28FED4. So we moved forward 4 bytes in memory just by adding 1 to this pointer. If the pointer was a double type pointer instead of an int, and a double has 8 bytes of memory, right? And you add 1 to it, instead of skipping forward 4 bytes, it would have skipped forward 8 bytes. So with pointer arithmetic, you're moving around in memory, and the compiler handles all the details in the background about how many addresses to move forward. Does that make sense?
Yeah.
Yes.
So it's that we got a random number because we didn't put any value in that memory.
Correct. We get this funky, weird number because we never stored anything in this address. And this is just leftover memory from whatever program was using this beforehand. Yep.
Why wouldn't it add the maximum value of 4 bits to 5?
Why wouldn't it?
Like because we skipped 4 bytes, right?
Four memory spaces.
Memory spaces. Why wouldn't add what's the maximum number I can put in there and then add it to 5? And in order to get a number. Why would it? I mean, I understand, but why would it use any other memory that it was stored in the same location before? That's how C++ works. That's what.
Are you just saying why is this like a random number?
Yeah, basically. Yeah.
Why is this just a funny random number?
Exactly.
So sometimes programs don't clear out their memory when they're done using the memory. They just exit, and whatever was left there. This may not even really be a value. This could be an instruction that just shows up as this number. But
I got you.
anyways, it is just garbage memory. So So that's pointer arithmetic. You can add any value to a pointer. Now check this out. What if I do this? Let me add 1,000 to it. I'm gonna move 1,000 integer spaces ahead. That means I'm gonna move 4,000 memory spaces forward in memory. What's gonna be there? You know, I mean, remember this is our little tiny little local piece of memory where I've created a couple of variables in my program. And then I'm gonna move 4,000 memory spaces forward ahead in memory and just go and see what's over there.
System over.
So what I'm saying is, like, we're introducing this new tool, the pointer, and with it comes great responsibility. You have the ability, we've just introduced a new tool to you for you to be able to push a pointer around anywhere in memory in your computer and start probing around and seeing what's happening there. And if you're not careful, you can do some real damage. So let's go ahead and let me close this, and then we'll run it again. We'll compile. We'll run this thing, and there it is. Now I'm 4,000 memory spaces forward. So instead of 28 FED0, now I'm at 29 0E70, which is in hexadecimal. That's 4,000 memory spaces ahead of this number. And I find some garbage information there. What do you know? Now, right now what I'm doing is fairly harmless because all we're doing is pushing the pointer somewhere else in memory and then asking what value is there. But if I started changing the values there, I could get into some real trouble, right? Yes?
So can you technically like write code for a pointer and then like use a pointer arithmetic to it and push it to a different memory space so you change the information there?
Right, right. This is a sneaky way you can actually get into other programs and go and start tinkering around with stuff in there. It's just, you're sort of getting into like hacking territory with this notion of pointers. So, you know, the reason I go through this discussion and spend a little time on this idea, one is you got to know that pointer arithmetic exists because that stuff is used in a lot of different settings for certain data structures. A linked list is an example of that. If you take the second course in this programming sequence, we do this kind of stuff with linked lists sometimes. And that's a certain kind of data structure that uses pointers to access each element in the list. But anyways, I also go through this, spend a little time talking about this so that we can actually address the fact that there's, you really have some power here with the pointers. You can push into some spaces in memory that you're really not supposed to be in, and make sure that you are mindful about what you're doing with pointers so you don't write programs that crash your computer. Sound good? Okay. By the way, if this arithmetic is supported, they also have the P1++ is also supported. So if you want to move the pointer to the next integer space forward, just do a P1++. You want to go one space backwards, P1 minus minus. So those operators work with pointers. Is that okay?
Like P1 means the initial output.
Yeah, this means the same as P equals P plus 1. Yep, same exact syntax. Or same outcome, different syntax. Although let's go ahead and run it, just because I'm curious. Yeah, and there it is. And we get the same thing. 28 FED0, add 1 to the pointer, and it's 28 FED4. Sweet. How about this? Let's do a P1 minus minus, just to see what's there. What's one space behind us in memory? So let's build that and run it, and there it is. Some other garbage memory. Huh. I wonder where the heck X2 is. Did we make X2? Oh, we never made X2. Oh no, we did make X2. Well, where does X2 live at? X2 lives, or let's just leave this one. X1 is here. and let's copy this. This is one of the things I really like about programming is if you're not sure what's happening, you can almost always write a line of code or a couple lines of code that'll go and test for what it is what question you have. X2 lives at hex 28 FED0, and X1 is at FED4. Isn't that interesting?
Shouldn't.
And now people, check it out. Check it out. When we did, right now we, back in our program, we actually did a P minus minus right here. P1 minus minus. After it was pointing to X1, right? And so it was pointing to 28 FED4. And then I did a P1 minus minus, and that actually goes to X2. X2 lives at FED0, so 4 bytes less than FED4 gets you to FED0, and we see the value is minus 10. So that actually illustrates the fact that the memory in my computer, at least the way this program is using it, is little endian, where like I create one variable, x1, and it's stored at memory location here. Let's call it 1004. And x2, which is created later, is stored one memory space up at 1000 or FED0. Right? So sometimes your memory is not stored in increasing order. Sometimes it's stored in decreasing order. That's called little endian. All right, let's then look at pointers and arrays. A pointer can point to an array, and you can point to any element in an array. So let's say we just we make a pointer here. Point to an array. So let's just make an array A. Make an array of integers. We'll call it A. Let's make it 5 integers big. And we'll set it to the values 0, 1, 2, 3, 4. Great. There it is. And now I'm going to take P1. I'm going to point to, I could do it two ways. We could say point to A of 0. Like this. A of 0 is an integer. P1 is an integer pointer. We're taking the address of A of 0 and storing it in P1. Okay? You okay with that?
Hey, Professor,
Yes.
did you comment out the P1 minus minus? Is that still there?
It's still there. It's not really going to matter a whole lot because we're going to take P1 and then point to A0 right after that.
Okay.
Yep. Okay. Another way to do it is just this. P1 equals A. These are the same things. These two things, lines 41 and 42, do exactly the same thing. They point to the very first element in the array A. This one, you have to use the reference operator because A of 0 is an integer, right? So you have to say the address of an integer I can store in a pointer. A by itself is not an integer. A by itself is the identifier for the array. It's the variable name of the array, and it itself is an address. So you're allowed to store an address right into a pointer, and that will always point to the top of the array. So this one always points to array top. The one above it, you can choose which array element to point to by the index that you provide. In our case, it was 0. Okay? Now, if you want to do something with that array, let's just go for int, or let's just do, let's just do for int n equals 0, n less than 5, n plus plus. We're just going to let this run a bunch of times. And now what I'm going to do is something like cout of star p1 let's see, hang on here. Star P1, and then, and maybe with like an end line or something like that. And then I'm gonna do this, P1 plus plus every time through the array, or every time through the loop. So this, the first line prints out the nth element, and the next line points to the next element in the array. So this is a for loop that runs for the length of the array, and instead of using the array identifiers to print out these, we have a pointer that points to it, and so we're gonna print out the dereferenced value and then increment the pointer to point to the next array space. Yes?
Won't it point to the next space in memory and not the next space in the array?
It points to the next space in memory, and that may be this way. Let's try it out and see how it goes. If you wanted a graphic on this stuff, here's what this looks like. Let's say your array is here. We start pointing to the top of the array, and then every time through the loop, we move the pointer to point down to the next element.
So it should print out 0, right?
It should print out 0. Let's try it.
What do you do with your n in the loop though?
We did nothing with n.
Why?
We
you
just needed a for loop to run 5 times.
Okay, that's it.
And we could use n if we wanted, or we could not. And in this case, we don't need it. I'm going to show you another way in a second where we will use it, and I recommend that way instead of this way. Okay, so there it is. Here we printed out 0, 1, 2, 3, 4. We printed out all of the elements in the array by the pointer. Okay, sweet. Sounds good. The problem with this approach is that by the time you get to the end of the loop, your pointer is pointing down at the bottom of the loop. Okay, so let's say I wanted to like run that code again and print out everything in the loop again, right? So then let's say I have a function that has this code wrapped into it, or I just want to copy the code again, right? And I'm going to run it again, right? Everybody with me? We're going to print the array again. Okay? What's the problem with this though? What issue am I going to run into doing this?
It's going to be pointing inside of the array.
Correct. So by the time you print the array the first time, and when you're done with the end of the loop, the pointer is going to be pointing to the bottom of the array, not the top anymore. So when we go and copy this code and we try to run it again, you run it, and oy, there's the array, and then it starts printing out some other stuff. You notice that the two next spaces are -10, that's x2, 5, that's what x1 is by this point in the program, because we changed it at some point. It started out as 25, and then we changed it to 5. And then there's just some garbage stuff down here. So this approach is not that great because the pointer doesn't stay pointing to the top of the array.
If you do p1 equals n, p1 plus n, isn't that better, kind of? Like just because you're actually you're making p1 equals the next value with n, and then you're printing it out again.
Correct. So what you could do is you could say, how about the dereference p1 plus n, like this, and then just take out this line. Right? Let's try that. Oops. Try that again. So everybody see that? We've now taken P1 and we've left it. We haven't changed its value anymore. P1, we took out the P1 plus plus. So now P1, our pointer, is just always pointing to the top of the array, and we're just going to add n to it every time through.
Just to,
Yep. And so if we run that, there we go. We've got the array printed out
twice.
0, 1, 2, 3, 4, and then the second time comes around. This is still doing the old way, but P1 is pointing to the top of the array still. So that's an improvement. And let me show you, since that's an improvement, and programmers like to be able to do that. Let me show you this syntax. Whoops. How about this? P of n. Done. So pointers, because they're like arrays, they have natively in C++, the array subscript operator, the brackets, are designed to work with pointers. And so once you're pointing to an array, you can actually just say, give me the nth element in the array. It works just like the array notation. So if you're used to the array notation and that works for you, boom, there you go. Just use that. You don't even have to dereference it. It does the indexing and the dereferencing for you in one step. Yes, Johnny?
Another question, for this time you didn't say, I mean, for example, the star P1 or star P something, how they know we're going to pointer to P.
Right. Like, you mean like we didn't use a star in front of it?
Yeah.
Right. So the star is used to dereference a pointer to get it to the value of what it's pointing to. And when you use the subscript operator with pointers, it does both for you. It goes to the nth value in the array and dereferences the pointer. So you don't need the star, is what I'm saying. The star is not needed when you use the array subscript, the square brackets. When you use the square brackets, you don't need the star. Does that answer your question?
Yeah.
Cool.
Thank you.
That's
supposed to be P1.
That's supposed to be P1.
Yeah,
Sorry.
exactly.
Sorry. In this case, it's P1.
So
Okay.
you need a lot of paper, like writing, to keep track of your pointers. That's what I understand from right now.
Yeah, it helps to kind of draw some of this stuff out first times through. Okay, let's finally get to talking about like where this stuff is useful. Okay, so let's remind ourselves about how declaring variables works. When we have a program and we declare some variables, x and y and z, maybe we make a double pointer called p or d, or I think that's a p. All of these are created at compile time. In other words, they're created, the variables are given names before the program is ever run. In fact, while it's being compiled. And they get memory spaces. Let's say, for discussion's sake, x lives at 1000, y lives at 1004. Z is a double, so it's 8 bytes in size. So it lives at memory location 1008 and 1012. Both of them, right? It takes up 2 4-byte blocks. Okay with that? And then your pointer lives somewhere else. We create a double pointer called P, and it lives somewhere like, let's say, for discussion's sake, at memory location 1024. Okay, so all of these variables, x, y, z, and p, are all created statically before the program is ever compiled. And they are what we call static variables. Once the program starts running, they are married to the memory space that they were given for the entire duration of the program's running time, its lifetime. Okay? We now introduce a new kind of variable, or a new kind of memory allocation. If not done statically, that is only once before the program's compiled, it's done what we call dynamically. While the program is running, we can go and ask for more memory as the need comes up. So like if you're running an application on a phone, right? And you got a folder somewhere to store all the photos that you take, right? Then a user comes along while the camera application is running. They launch the camera thing. Here I am, I'm getting ready to take a picture, and I go ahead and push the click button to take a picture. Enough memory now needs to be allocated to store that picture in that folder, right? In that space. That is a changing memory usage, what we call dynamic, because it changes. So the way that we allocate, we ask for new memory in C++ is with the new keyword. This keyword, when the compiler encounters this keyword, it says, oh, you want some new memory. How much memory do you want? Oh, you want enough space to store one double. Okay, And so you make a request to the operating system. You say, operating system, my user has done something or my program has decided that it needs more memory. And I need enough space to store one double, 8 bytes of memory. The operating system says, okay, sure. I'll go and check the stock and starts looking through and says, oh, you know what? This part of memory isn't used very much. Oh, yeah, that's the one. I'm gonna go find this address, and comes back to your program and says, here you go. You can have this address and you can do anything you want with it. It's 8 bytes in size, and do whatever you want with it. And we say, oh, thank you, operating system. We'll take that address and we'll store it in a pointer. Sound good? That's all of what happens behind the scenes every time the compiler sees this line of code, a new request. Got it? We ask for new memory, we tell it how much, the compiler goes and finds it, gives it back to us, and we store it in a pointer. And again, the type of the pointer here must match the type of the memory that you're requesting. So that's why, in this case, we have a double star type for P, because we're asking for a double. Questions? Henry, your question?
Wait, so 12.5 doesn't live at where P is?
Wait, say that again?
12.5 doesn't live at, like, address 1024?
No, 12.5 does not. We're going to show that in a second. Right now, all we've done is we've just we've created the pointer, we created the pointer up here, and it lives at memory location 1024, let's say, for discussion's sake. And then we ask for the new double. The operating system goes and finds it. It finds this piece of memory here, which is got the word new double next to it. It doesn't have a name next to it, like X, Y, Z, P, because it cannot have a name, right? Everyone agree that we can't assign a name to this. Why can't we assign a name to it? How come we can't give a name to this piece of memory?
Because the compiler will create space in memory, which it will be assigned as soon as you run the program.
Right.
While here we're asking the OS to give us space in memory.
And while the program is already running, right? So the issue is that the program is already running. You can only name a certain memory space before you compile a program. And if the program is already running, then we can't give it a name. Okay? So so then P now points to this nameless memory that's going to live somewhere. Wherever it lives, we don't really care very much most of the time. We just care that it's there. And so now when we do something like star P equals 12.5, we can actually store something into this memory. Or if you wanted to let a user type something in, you could do something like let's say it was kind of similar to taking a picture or asking for a new piece of information from a user, right? So you could do something like cin into star P. And that would allow a user to type some information into the console, and then that information would come here into this variable. Okay? One optional default initialization you can do if you want. If you want to create a new double piece of memory and you know what you want to initialize it to, like let's say you wanted to initialize it to pi for some reason, right? You do this all in one line. You can say P equals new double parentheses and put in whatever value you want to initialize the new memory to. This is optional. You don't have to do it this way. It's just another feature that's supported.
So will there be 2 new pieces of memory now?
If I did do that, yes. If these were in sequence, yes. Now here's a problem. So let's say we had another new piece of memory. We list it over here. Here it is. And it has the value pi in it. Okay, this is another new double. Okay, and let's say P no longer points to here, P now points to here. Right? That's what would happen if you ran both of those lines of code. You said P equals new double and you did some stuff with it. And then you said, oh, P equals new double again. And what happens? The operating system goes and finds you new memory, another new double. You get to initialize it to whatever you want, and that's great. And all this is fine. What's the problem with this? What happens to this memory when the pointer goes and points to the new memory?
Still there.
It's still there. And it's still being used by your program. The operating system thinks that you still are using it because you never told it otherwise. This scenario is a serious problem in any computing architecture. And it's called a memory leak. A memory leak. A memory leak describes the fact that you're allocating memory and you do something with it for a little while, and then you don't give it back to the operating system. One of the specific problems here, since the operating system gave us this new memory, but we never knew where it was pointing to, or what value it was, and then we went and pointed to something else. As soon as I've done that, I've now lost this address where it lives. I've lost it forever. You can't go back and find what this was because we never saved. I never did something like, oh, save this pointer into a temporary other pointer so that I remember the address of where this was. Does that make sense? Remember how we're accessing this memory. Everything we do to it is through the pointer. And so if you change the pointer to point to somewhere else, you have no way of getting back to, without saving what this address was somewhere, you have no way of getting back to this and eventually giving it back to the operating system, which is called deallocating.
So
Yes?
we deleted P equals new double 3.14, would 12.5 be somewhere else then?
If you delete this,
Yeah, if you ran it and then you deleted it, and you ran it again, would 12.5 be somewhere else than the original spot?
hang on. So we're running this program just once.
Yeah, and then you delete P equals double 3.14.
Let's say you just say delete P. Let's actually get to that in a second. Let's talk about the delete keyword. So really what you want to do, let's say you were done with this pointer, P. You want to use what's called the delete keyword. The delete keyword is written before a pointer, like this, and that frees up memory. It releases the memory back to the operating system. So when you say delete P, that would then sort of, you can think of this like, poofing into thin air or something like that, and all the data, this memory is given back to the operating system. The important thing for you to recognize is that deleting P does not delete the pointer itself. The pointer still exists. P still exists, and it can point to something else. But deleting P just releases whatever memory it was pointing to. P itself is a static variable. You can't delete it. So the thing to do in addition to P is then, after you delete P, free up the memory, set P equal to null.
What?
So you set it equal to 0. Null is 0. At an address of 0, there's nothing there. And this is a standard implementation that is always done every time you delete a pointer, and if you don't have something to point to right away, set the pointer to null. We'll come back and talk about why that is on Wednesday. And yeah, and I'll see you guys then.
Sure.
Great, thank you.